This video is going to go over running the MinSeg Motor Simulink files. The first thing you need to make sure is that rasp-lib is installed properly. The rasp-lib folder and the startup.m file both need to be located in the Documents MATLAB folder. If you look at the contents of rasp-lib, you'll see the actual library in there and the examples folder. The startup.m file located in the MATLAB folder adds all of the folders in rasp-lib so it knows where those files are located. All of the Simulink files are in the M2V5 365 40mm Quick Start folder. So if we navigate into that folder, we can find the only M file that will run and plot all of the examples. So we can open that file and then run each of these cells to run and plot the results. Before we do that, all of the Simulink files are set up to use COM port 89. The easiest way to set up your system to use all of these files without having to change each of them is to just change whatever your COM port is for your device when you plug it in. So the first thing to do is open Device Manager and then look at the ports. When you plug your device in, you'll identify what COM port gets added. Most likely it won't say Arduino Mega, it'll say CH340 or PL2303. But once you've identified what the device is, if its COM port is not 89, which it most likely is not, then you can right click this, go to Properties, Port Settings, Advanced, scroll all the way down from the beginning to COM port 89, then click OK, OK. Disconnect the USB device, plug it back in, and make sure it comes up as COM port 89. Once it's set up as COM port 89, once you have rasp-lib installed, the startup.m and rasp-lib folder, both in the MATLAB folder, then you're ready to run each of these experiments. Now we will go through and run each of these cells. The first cells, if I push Control Enter, will define the supply. That's the maximum voltage supply your USB is capable of supplying to the motor. This first ramp response file shows you how to find out what that is. And then we have the encoder conversion. So first we'll run the ramp response. If I go into the cell and press Control Enter, it will open the Simulink file that's going to be run. And it should open up the scope, and we're going to observe the results from the webcam. So if you want to run first finds V supply, comment this out, uncomment this block, and then just run this file. This will turn the motor fully on, and you have to measure the voltage that is between each of the motor pins, because this will identify, if the motor is fully on, how much voltage your computer is capable of supplying to the system. This is used to properly scale the voltage that's used in the motor driver block. In this example, we're just running a ramp input. We're going to very slowly increase the voltage and observe the speed of the system. This will allow us to calculate the steady state gain and some other parameters. So here we can see the motor doesn't start spinning until approximately 0.5 or 0.6 volts, and then its speed increases linearly as we slowly vary the voltage. Once the simulation gets up to about 48 seconds, because that's the maximum voltage my USB has, is around 4.8 volts, the simulation will stop and it will close, should close these diagrams, and it will plot those results. It also plots all of the data after it's spinning, so you can identify the steady state gain by going to basic fitting. Since it only plotted the linear part of that, we can plot the second data curve and do a line fit, and this will help identify what our speed versus voltage slope is. In this case, the steady state gain is 61 radians per second per volt. So that first ramp response can be used to identify the steady state gain as well as the voltage at which the motor starts spinning. So it starts spinning around 0.6 volts. This will be important when we do control later. The next test is to perform the step response. From there we can calculate the steady state gain again or verify it, and we can calculate tau. So here we will run the motor step response Simulink diagram. It opens up the step response. This is going to go from one steady state speed to another steady state speed, and it will plot the results. It's important to note that you have to specify or have V supply defined, because inside this block, we'll use that to appropriately scale the voltage. You can always check the compilation status by clicking on View Diagnostics. Here we can see it's successfully compiled all of the files. We can see how much memory it uses, and then it will download to the board and run the test. So here it's going from one steady state speed to another. When the test is done, it will plot all of those results. I guess we have to go to the next cell to plot those results. It shifts all of the data so we can see how consistent each one of those steps are. So it's very consistent. Then from our previous identification, we can estimate what K is, we can estimate what tau is, and you can adjust these for your motor, and then it will plot this on top of that to show how well our model matches our experimental data. Now that we've used the step response to identify the motor parameters K and tau, we could design a controller. In this case, we're going to do a simple proportional control, and we're going to use a proportional gain. That's the maximum that will avoid saturation of our 4.8 volts that's available. Here it's important to specify the voltage that the motor initially starts spinning at. That's because in order to get a good match for our theory, we're going to want to account for this deadband. So the system's always going to be applying 0.6 volts to the system to take care of that coulomb friction. So here we're going to be running the position control. So this is simple position control. If you open up this motor block and you open or double click on the motor driver, you can see that it will use the V supply, which for this USB is around 4.8 volts. And it will also be adding the voltage offset, which is the 0.6 volts. That's to account for the coulomb friction that's present in the system, and that was determined from the ramp response. So here we can see the position response. We could have lined the wheel up initially so that the 0 was lined up so we could see how well that performed. We could do that quickly. Line up the 0 and then run this test over again to see how well the position control works. It's fairly well lined up here. And we can check the build status here. You can see this is pretty accurately going back to 0 degrees. We have significant overshoot because we're using a high gain. Then we can use a model to compare that. So that's all the data and all of the plots. Again, it's very consistent between each of the plots. The green is a pure linear model. So we can see that in terms of percent overshoot, it's reasonable, but these other peaks don't really line up. If we add the fact that we're adding a voltage offset from our compensator, we get a slightly better match, which is the red line. And then if we have a Simulink diagram that includes simple coulomb friction, so this is somewhat ad hoc. So this includes our compensator voltage offset. It has our simple first order experimentally determined transfer function and a simple estimation of coulomb-like friction. So if we include that coulomb-like friction, then we get a fairly good match between the simulated response and the actual response. So that's the position control. Next, we'll perform position control. So in this case, it appears the reference is going to go from 0 to 200 radians per second. We're going to use the maximum gain of Kp again. And this is going to be the theory. So this is going to predict the speed control. So it wants to go to 200 radians per second. We'll be anticipating significant steady state error at this gain. And then we can run the hardware speed control. So now the hardware system has been modified so that the output is speed instead of position. And it's just simple proportional control. And it's going to go from 1 steady state speed, in this case is 0, to 200 radians per second. So we see it goes to 120 radians per second, down to 0. And it's a pretty good match from our model versus experiment. So we did get that anticipated steady state error. So next we're going to address that steady state error by applying pure integral compensation. So my compensator is proportional gain and a pole at the origin. The theory for that then predicts, looks like have a very small amount of overshoot, but it will now get rid of the steady state error and go up to 200 radians per second. The system's speed is significantly slower than the previous response. The previous response was around, the settling time is around 0.1 second. Here we see that adding pure integral control significantly slows down the system by, in this case, a factor of 5, but it does get rid of the steady state error. Now we can run that hardware test. And we can see that it's now going up to the desired steady state speed, but it's significantly slower. And there's a very good match between the prediction and the experiment. Finally, we'll be doing PI compensation. So to try and recover some of this lost speed, we'll add a 0 to the system. That's a PI compensator, pole at the origin, and a 0 somewhere else. So we're going to predict what this PI compensation is. The speed is increased a little bit. So now it's about 2 times, instead of 5 times slower, it's around 2 times slower than the uncompensated system that does have steady state error. This is what our prediction is, and we will run the hardware model. So this is proportional control, and now I'll be adding a 0 to the system. So this is a PI compensator. And we can see, oops, figure 7. I guess we have to plot that. We can see that there's a very good match again between the experiment and the prediction.